Imagine for a second that you are the lead executive at a massive consumer goods company.
Okay, high stress job.
Right, high stress. And your team brings you this brand new product formula. They tell you, they tested it, and 60 people in a room just absolutely loved it.
60 people.
Just 60 people. And based on that one room, you are now expected to greenlight a $50 million global product launch.
Wow.
Yeah, I mean, it sounds terrifying, right? But the crazy thing is, every single day, massive corporate decisions, public policy shifts, medical breakthroughs, they are all driven by these like tiny fractions of data. And the real question is, how do you know if those 60 people actually represent the whole world or if you just made a $50 million mistake?
That's really the multi-million-dollar tightrope walk of quantitative analysis. But, I mean, we actually intuit this concept on a small scale all the time.
What do you mean?
Well, think about when you buy like a large bag of rice at the grocery store or market.
Yeah.
You scoop up a handful, you run a few grains through your fingers to check the quality, right?
Yeah, totally.
And then you make a purchasing decision for the entire huge bag based on that one tiny handful. You just naturally assume the handful represents the whole.
Right, right. Welcome to this deep dive, by the way. Today, our mission is to basically scale that intuitive grocery store habit all the way up to the corporate boardroom.
Exactly.
We are unpacking the really rigorous methodologies behind sampling and sampling distributions. The goal here is to shortcut your way to being incredibly well-informed on how these high-stakes decisions are mathematically justified.
Because they have to be justified.
Right. So we are going to explore why we are literally forced to rely on fractions of data. Then we'll get into the intense rules behind how we actually pick that data so we don't, rig our own game.
Which is very easy to do accidentally.
Totally easy. And finally, we'll look at the ultimate mathematical lie detector test that separates a genuine breakthrough from, like, a total fluke.
I love that. And to really grasp the gravity of this, we first have to discard the assumption that more data is automatically better.
Wait, really? Because it feels like more is always better.
Right, on the surface. Complete enumeration, what statisticians call a census, where you literally measure absolutely every single entity in your population. That feels like the only way to get perfect information.
It definitely seems like the bulletproof approach. Like, if a banking corporation wants to understand the morale of its 30,000 employees spread across, I don't know, hundreds of branches, surveying every single person guarantees you haven't missed anyone.
Sure, but consider the actual logistics and the timeline of that complete census. You're sending surveyors to hundreds of remote branches. You're conducting 30,000 interviews.
That would take forever.
Exactly. Processing that ocean of data could take, 6 to 8 months? By the time you finally interview that 30,000th employee, the morale of the very first branch you visited has probably shifted completely.
Oh, wow. I didn't even think about that.
Yeah, I mean, the market moved, management changed, maybe a new competitor arrives. The population is just far too dynamic to capture in its entirety.
So it's basically a moving target.
Precisely.
Yeah.
So surveying a rigorously chosen fraction, say just 250 employees, is not just vastly cheaper, it actually gives you a more accurate snapshot of that specific moment in time.
Okay, let's unpack this with a different angle because time and money are obvious constraints. But what happens when complete enumeration is literally physically impossible?
Oh, the destruction dilemma.
Right, like if you want to know if a cake you baked is good, you cannot eat the entire cake to find out. Or there is absolutely nothing left to serve at your party.
Yes.
Complete enumeration literally destroys the product.
That's a great analogy. In quality control, we see this all the time. Take a factory that manufactures fluorescent light tubes.
Okay.
The only way to definitively test the total lifespan of a fluorescent tube is to plug it in and burn it until the filament fuses and the glass goes dark.
Obviously.
So if the quality control department demanded a complete census to ensure every single tube met the, say, 10,000-hour standard, they would have to destroy their entire inventory.
You would have mathematically flawless data.
And a warehouse full of shattered glass.
Yeah, with absolutely zero product left to sell.
Exactly. In that environment, pulling a sample of 15 tubes off the assembly line and judging the entire month's production run based on them isn't like some lazy shortcut. It's the only mathematical and physical reality available.
You are literally forced to sample.
You are forced.
Which brings us to a massive problem. If we are physically and economically forced to judge the whole by a tiny fraction, how do we choose that fraction without completely warping the reality we're trying to measure?
That is the big question.
Because, I mean, human beings are fundamentally terrible at being random.
Mhm.
If you tell me to randomly pick 15 files from a cabinet, I am absolutely going to subconsciously pick the ones at eye level.
Or the ones right in the front.
Yes.
Yeah.
I'm not reaching to the dusty back corner.
No, of course not. Human intuition is honestly the enemy of pure data. And that is exactly why quantitative analysis relies on the strict, unforgiving rules of probability sampling.
Probability sampling.
Yeah. In probability sampling, you remove human whim entirely. Every single element in your population must have a calculable, non-zero probability of being included in the sample.
Meaning everyone has a fair shot.
Right. The decision is handed over completely to cold, mathematical chance.
So the conceptual baseline for this is simple random sampling. It's the classic names in a bowl idea, right?
Exactly.
You write everyone's name on a chit of paper, mix the bowl thoroughly, and draw blindfolded. Every chit has the exact same odds. But you cannot put 30,000 bank employees in a mixing bowl.
No, you definitely cannot. So you scale it up using external tools that force randomness, like a random number table or a computer generator.
How does a random number table actually work in practice?
Well, you assign every single employee a serial number, say 0001 to 30,000. Then you use a pre-generated grid of completely random digits to select your targets. And the rules for reading that grid are ruthlessly strict.
To protect the integrity, right?
Right. You have to declare your path before you even look at the numbers. You decide, like, I am starting top left, and I'm reading 3-digit sequences moving straight down the column.
Okay, so no changing your mind halfway through.
0. If your population stops at 899 and the table gives you 934, you don't adjust it. You don't round down to 800. You discard it completely.
Wow, just throw it out.
Yep. And if you hit a number you already selected, you discard that too, because sampling the same person twice warps the representation of the remaining pool.
I mean, that sounds incredibly tedious, like a really manual process.
Tedious is the perfect word for it. And in a fast-moving business environment, reading thousands of random digits to build a sample list isn't always practical.
So what's the alternative?
Statisticians developed a shortcut that retains the mechanics of chance, which is called systematic sampling.
Okay, let's look at systematic sampling. Let's say I want a 1-in-7 ratio for a business study on retail foot traffic.
Okay, good example.
Instead of dealing with random number tables for every single selection, I just use chance to pick a starting day between 1 and 7. Let's say chance dictates I start on day 2.
Right.
From then on, I automatically pull every 7th day. Day 9, day 16, day 23. I mean, it completely bypasses the tediousness while still feeling random.
It is incredibly efficient. But walk through the actual schedule you just created. If your initial random draw lands on day 2.
Day 2 is a Tuesday. Then day 9 is a Tuesday. Day 16 is, wait, every 7th day is a Tuesday.
Exactly.
I would literally only be measuring Tuesdays.
You would. And if you were measuring retail foot traffic, you have just built a mathematical model of the world that completely ignores the massive Saturday afternoon rush.
Oh my gosh.
It ignores the Sunday closures, the Friday payday spikes.
Okay.
Your entire worldview is just Tuesdays.
That's hilarious, actually.
This is known as periodicity bias. If your sampling frame has a hidden rhythm or pattern that lines up with your sampling ratio, your shortcut just destroyed your data's integrity.
That is such a brilliant trap to fall into. The arrangement of your list actually dictates the truth of your sample.
It really does.
So simple random sampling and systematic sampling operate on the assumption that you have this uniform, neat list to pull from. But the real world is incredibly messy.
Very messy.
Real populations are divided, they're fractured, they're chaotic.
Which is why, when you are dealing with a complex, divided reality, you have to change your strategy. You move from simple pulling to slicing the pie, using methods like stratified sampling.
The stratified samples?
Yeah. The goal here is to increase your statistical efficiency by acknowledging those deep divisions in your population. You divide the total population into mutually exclusive groups called strata.
Okay, let's ground this in a real scenario so it makes sense. Imagine a beverage company wants to estimate the demand for a new premium iced tea in a massive residential city.
Okay.
They know that income heavily dictates beverage spending. So instead of randomly sampling the whole city and accidentally interviewing, like, only broke college students.
Which could easily happen by chance.
Right. They divide the city into 3 strata: high income, middle income, and low income households.
Because the underlying assumption is that families within the same income bracket, within the same stratum, will have relatively similar purchasing habits.
Right.
They are homogeneous inside their group, but highly distinct from the other groups. Once you separate them, you pull a simple random sample from inside each individual stratum.
It is exactly like doing laundry. You don't just reach into a massive pile of clothes in the dark.
I hope not.
Right. You separate the darks, the lights, and the delicates into their own distinct piles first. And then you pull a few items from each pile to ensure you have a perfectly representative wash.
That's a perfect way to visualize it.
Now, if half the city is middle income, and you make sure half your sample is middle income, that is proportional. But where this gets really powerful and a bit mind-bending is when you look at disproportional sampling.
Yes, disproportional sampling is entirely driven by variance.
Which is what?
Variance is the measure of how wildly the behavior fluctuates within a group. Imagine your low-income stratum has massive variance. Some families buy 0 premium beverages, while others occasionally splurge and buy a dozen for a party.
So the behavior is chaotic and unpredictable.
Highly unpredictable.
But the high-income stratum is completely predictable. Let's say almost every single high-income family automatically buys exactly 5 premium iced teas a week. Without fail, the variance there is near 0.
Exactly. So in that case, it would be a phenomenal waste of resources to survey 1,000 high-income families because you are just going to get the exact same answer 1,000 times.
5, 5, 5.
Right. Instead, you sample disproportionately. You interview only a tiny handful of high-income families because their predictable behavior is easily captured.
And then what?
You pour all your remaining survey resources into heavily oversampling the low-income families to map out that wild, chaotic variance.
Think about the data you rely on in your own career, for those of you listening. Are you constantly oversampling the safe, predictable parts of your business while starving your data collection in the high-variance, chaotic segments that actually need the most scrutiny?
It's a really common mistake.
Yeah.
That is the power of stratified sampling. It allocates your attention where the statistical mystery actually lives. But it is also incredibly expensive to map out an entire city by income before you even start surveying.
Yeah, getting that data up front has to cost a fortune. Which leads us to the gritty alternative, cluster sampling.
Yes, cluster sampling.
If stratified sampling is meticulously separating your laundry by color and fabric type, cluster sampling is just walking into a room, grabbing one entire laundry basket at random, and hoping the mix of clothes inside roughly represents the whole house.
I love that. With cluster sampling, you basically trade statistical perfection for geographical reality. Instead of dividing people by their personal traits, like income, you divide a massive city into dozens of geographic blocks or neighborhoods.
Those are the clusters.
Those are your clusters. You randomly select to say 3 of those blocks, and you survey every single household inside them.
But a cluster should ideally be a mini version of the whole population, right?
Right.
It should have a messy, heterogeneous mix of high, middle, and low incomes living relatively near each other.
Ideally, yes. The trade-off here is pretty stark, though. Cluster sampling is statistically weaker than stratified sampling because the 3 blocks you randomly pick might coincidentally have a weird local quirk.
Like maybe a new trendy cafe just opened on that specific block and warped their beverage habit.
Exactly. But it is vastly cheaper. You save an absolute fortune on travel and logistics because your survey team is just walking door to door down a single street rather than crisscrossing a sprawling metropolis to track down specific income brackets.
So in the corporate world, the available budget often dictates the math.
More often than not.
And what happens when that budget is almost 0? Like what happens when you don't even have a map of the city to create your clusters? This throws us entirely out of the gold standard of probability, right?
Oh yeah, you enter the Wild West of non-probability sampling.
Non-probability sampling.
Yeah. Here, you abandon the rule that every element must have a calculable chance of being selected. You are no longer insulated from human bias. Selection is based purely on convenience, quota, or executive judgment.
We see this everywhere, honestly. Convenience sampling is, standing outside a specific shopping mall at noon and interviewing whoever happens to walk past.
Yep.
Judgment sampling is an executive handpicking a few extreme client cases to study. And quota sampling is telling a surveyor, I don't care how you find them, but bring me responses from 20 tech CEOs and 50 gig workers by Friday.
And because it lacks true randomization, you cannot mathematically calculate your margin of error.
Yeah.
It's impossible.
So why do we ever do it? If probability sampling is the mathematical ideal, isn't convenience sampling just inherently lazy and dangerous? Why would anyone risk capital on unquantifiable data?
Because, frankly, building a sampling frame like a comprehensive, accurate master list of every single resident in a massive city might cost 10 times more than the actual product you're trying to launch.
Oh, wow. The list itself is the barrier.
Yes, and sometimes the population is so hidden or niche that you have to rely on an expert's judgment to find them at all. Furthermore, what drives the need for a massive, rigorous sample isn't the total size of the population, it's the variability.
Wait, elaborate on that. The size of the total population doesn't dictate the sample size?
It really doesn't. It is a profound statistical truth. If a population has absolute zero variability, meaning every single entity is fundamentally biologically or chemically identical, a sample size of exactly 1 is perfectly accurate.
A sample size of 1.
1. If you want to test the salinity of the ocean, you don't need a million-gallon sample. 1 thimble of seawater gives you the exact parameter of the whole, because the salt is uniformly dissolved.
That is mind-blowing.
It is only the unpredictable variability of human behavior in complex systems that forces us to expand our sample sizes.
So the chaos dictates the cost.
Beautifully put, yes.
Okay, so let's bring this to the grand finale. You have navigated the budget. You avoided periodicity bias. You sliced your strata. You have your sample, and you ran your survey.
You survived the process.
You survived. You hold in your hand a result, a sample statistic. How do you actually prove that this number reflects reality and isn't just a weird, isolated fluke?
This requires the ultimate meta-analysis, the sampling distribution of the proportion. This is where statistical inference flexes its real power. Let's return to the corporate boardroom you mentioned at the very beginning.
The $50 million decision.
Exactly. Imagine your company has a legacy talcum powder product. Years of exhaustive historical data tell you that exactly 45% of the total market prefers your legacy brand over the competitor.
Okay, so that 45% is your population parameter. It is the established truth.
Yes, the baseline is 45. Now, your R&D department develops a new, cheaper formula. They give the old and new versions to a highly rigorous, randomized sample of 100 consumers. The results come back, and 60 out of the 100 consumers, so 60% of your sample, prefer the new formula.
I mean, if I am the executive looking at that report, I am thrilled. 60% is a massive jump from 45%. I am ready to greenlight the new factory. The data says we have a hit.
But a rigorous quantitative analyst will stop you right there.
Why?
Because that 60% is just a statistic from one single sample of 100 people. If you ran the exact same test tomorrow with a different 100 random people, you might get 48%. The next day, you might get 52%.
Oh, because of variance.
Right. The sampling distribution is the theoretical map of all possible samples you could ever take. And it allows us to ask the million-dollar question. Assuming the real-world truth hasn't actually changed, and the true preference is still sitting at 45%, what is the mathematical probability that we would accidentally pull a sample that hits 60% just by pure dumb luck?
We put the sample on trial against the known reality.
We do. And we calculate the exact probability. If the math tells us that the probability of accidentally getting a 60% result when the truth is 45% is quite high, say a 0.4 probability, then your 60% result is completely meaningless.
It's just noise.
It is just sampling error. The new powder isn't actually better. You just happen to randomly grab 60 people who love the new scent. You do not build the factory.
But what if the probability calculation comes back microscopically small? What if the odds of accidentally pulling that 60% result are like 0.001?
Then you have cornered the truth. You are faced with two choices. Either you just witnessed a near impossible 1 in 1,000 statistical anomaly, or your foundational assumption is wrong.
Meaning the underlying truth is no longer 45%.
Exactly. The population parameter has genuinely shifted. The new version actually is superior.
And that is how you authorize the $50 million launch. Not with a gut feeling, but by proving that the alternative explanation, pure luck, is mathematically impossible.
It provides a concrete foundation for corporate confidence. It's the mechanism that allows us to read the invisible forces of a massive world, using only the tiny fractions we can actually hold in our hand.
We have covered incredible ground today. I mean, we started with the sheer physical necessity of sampling, the destruction dilemma that prevents us from burning every fluorescent tube to test its worth.
Right.
We navigated the strict, unforgiving rules of simple, random sampling and discovered how a harmless shortcut like systematic sampling can trap us in an alternate reality of just Tuesdays.
A very dangerous alternate reality.
Yeah.
We explored how to strategically slice up a messy, divided reality, too, using stratified sampling to hunt down the high-variance, chaotic data versus leaning into the budget-friendly pragmatism of geographic cluster sampling when resources run dry.
And finally, we witnessed how the sampling distribution acts as the ultimate lie detector, putting our tiny sample on trial against the laws of probability to separate a genuine market breakthrough from a dangerous statistical fluke. So to you listening, the next time you are scrolling the news and a bold headline stops you in your tracks declaring 60% of consumers demand X or survey proves massive shift in public opinion, you are no longer a passive reader.
You know exactly what structural questions to ask.
Exactly. Was this a truly randomized probability sample, or did they just stand outside a convenient location? What did their sampling frame actually look like? Did they account for the high variance in the population, or are they hiding behind an illusion of precision?
The most profound takeaway here, I think, actually transcends business and data science. We established earlier that if a population has absolutely no variability, a sample size of exactly 1 is mathematically perfect, right?
Right. The thimble of seawater represents the entire ocean.
Exactly. Think about how often that mathematical principle plays out in our daily psychology.
What do you mean, like the N of 1?
The N of 1. How often do you make sweeping, ironclad judgments about an entire generation of people, a different corporate department, or a completely foreign city based entirely on an N of 1 your own single, isolated experience?
Oh, wow. We assume the handful of rice perfectly reflects the whole massive bag.
We navigate life assuming the world has zero variability, when in reality the world is chaotic, deeply fractured, and wildly unpredictable. Maybe the problem isn't the world. Maybe you just need a much better sampling method.
That is a brilliant and really challenging thought to leave off on. Next time you think you have something entirely figured out based on one experience, ask yourself what stratum you might be ignoring. Thanks for joining us on this deep dive. Keep questioning the data, keep checking your own variants, and we will catch you next time.